In this lesson, I will show you how to use Desmos to determine the relationship between two tested variables. I will spare you the time of entering the data, as the data table has already been created for you right here. We can see that we have a variable of x1 that we adjusted, and we had 4 different points that we collected. And there were 5 responding variables or dependent variables that were based off of this data right here. So we see that we have a purple set of dots. Okay, they are shown over here. We have black, red, blue, and green, and they're all matching the different variables that are given to them. Now, I'm going to hide a couple of these to show you how they work. Now, it looks like a big mess at first because we see dots everywhere, but if we don't plot everything simultaneously, it becomes a little bit more apparent what we're looking for. So I'm going to hide these at the moment. Now, if we take a look at our purple data set that is left, we see that we have a trend. There does seem to be some kind of effect of changing this independent variable and the responding dependent variable. We see that we have this inclining trend. The first relationship that we want to show you here, this is known as a direct relationship where we have this going up. So in Desmos, here's how you will determine your exact relationship type. In the box over here is where we're going to test for our dependency. So we are looking to see if variable y1 depends upon x1. And the way that we do that is just simply typing in y1, and we are going to use the tilde key, which is the key just below escape and next to the 1 on your keyboard. So we hit shift and it looks like a little squiggle. So we want to see here if y1 has a dependency on x1. And the way we do that is we type in the letter A. I use the capital A here. All right, I'd encourage you to do the same thing. Logger Pro will use the same letter. And we want to see if y1 depends upon x1, so we're just going to times it by x1. And what we see is that it forms a nice line that mostly goes through these points. Now, not all the points do go through because in most experiments, you're not going to get perfect data. But this looks pretty good. It seems that it makes a line that goes through most of the data pretty well, and it goes through the origin. One of the important characteristics that we're going to look for here is to try to get the graph to go through the origin if at all possible. And we will see that there will be times where that won't happen, and we'll explain that at a later time. Now, because this curve works, we are going to determine that this is considered to be a direct relationship. What this means is that if I double the x variable or the independent variable, I would expect the y variable to also double with it. I'm going to move this up right now to below directly proportional. So when something is directly related, it means that the y is directly related to the x by some coefficient. In this case, the coefficient was 2. All right, now we're going to look at our second set of data. Our second set of data that we're going to show, I'm going to hide this one, is our z data. We see with our z data that as the independent variable is increased, we see that the dependent is seemingly decreasing as time goes on, or I shouldn't say time, as the independent variable is getting bigger. Now, we do the same exact thing, but if we try to see how this is z1, how z1 is dependent, we're going to press z1, we're going to use the tilde key, we're going to use the same a, but this time we're not going to put the same exponent. So we're going to put x1 because we want to see if z1 does depend upon x1. And we see that this graph makes absolutely no sense. This line is not a good trend for this data here. So what we need to do is we need to manipulate some exponents to see how this works. Now, traditionally, if we have a positive exponent, it means that that term is a numerator term and it would belong up in the numerator of an expression. And if we use a negative sign, it would belong in the denominator. Negative exponents that are in the denominator means that as something gets bigger, something gets smaller. And that's what this trend is showing us. So we're going to try an exponent by hitting Control 6 will give me a caret. I'm sorry. Shift 6 will give me a caret. And I'm going to try the simplest of powers. That will be the -1 power, meaning to the first power, but in the denominator. And we see that this works quite well, that this is the curve that seems to fit this data well. If I were to scroll down and take a look, I do see that it gives me an a parameter, which is a constant, which we'll look at another video. But there is definitely a proportionality between these two, and this proportionality is considered inversely proportional. All right, I'm going to show you a couple other trends real fast to get through this video. So I'm going to hide this, and now I'm going to go back up, and now I'm going to look at my third data set. My third data set is the u variable. And if I take a look at this graph, I see that it is climbing, but not at such that diagonal rate. So I'm going to try this one again, doing the same thing. I'm going to see if u1 is proportional to the variable. So I'm going to try u1, I'm going to use a, And I'm going to type in x1 again because that has always been the same independent variable. And again, I see that that does not work very well. So I'm going to use my Shift 6 key to get an exponent. And I'm going to try an exponent. This next simplest exponent would be a 2. And if I click that, that does seem to work well. It does create what appears to be half of a parabola that does go through the origin, and it does seem to fit the data reasonably well. This relationship is known as a square proportional relationship, meaning that as the independent variable is doubled, the dependent variable is not only double, but it's double square, meaning it increases by a factor of 4. Okay, and this characteristic, or this type of graph, is characterized by this growing parabola. So I'm going to move that up to our square proportional relationship. All right, we have a couple others that can happen now. We've seen a couple exponents. Our third type would be this variable that we see going on here with V1. Now, V1, unfortunately, my last data point, 19.8, is hidden. And to spare you the difficulty of trying to find it, it's somewhere kind of up here under my name. We're just going to avoid changing this up, and I'll just show you how it works. So we're going to see if this next variable, sorry, I forgot its name, V1, we're going to see if V1 has a dependency. So what I'm going to do is do my tilde key again. I'm going to type in my A. I'm going to use Shift and 6 to get my exponent. Oops, I'm sorry, I'm a step ahead of myself. We're going to see if it depends upon x1. Again, that doesn't seem to work very well. But if I use my exponents, my next step that I can try, well, I tried square. The trend is still going up. So if it's going up, it can't be a negative exponent. So I'm going to try my next simple exponent. Now, 3 seems like it would be logical, but a cube root or a cube is usually not a very common exponent. So we're going to try our next mathematical power, and that's a square root. Square roots are designated by the half power. So I could do 1/2 or just simply 0.5. And if I do that, and again, one of my points is hidden here, I do see that this data fits pretty well. It does go through the origin. It bends through the data reasonably well. I have one point here that's not perfect, but overall this works pretty well. This is a parabola, except for in this case, the parabola looks like it's laying on its side. So what we see here is that the independent variable, as it increases, the dependent variable also increases, but the rate seems to get less and less and less as time goes on. In fact, we would say that when you quadruple the independent variable, that the dependent variable will only double. So this rate is greater than that rate. All right, and now finally we have one last one that's common in this class, and that would be our final variable. And if we take a look at that, that was W1. And if we scroll down, we see that W1 looks very much like that original inverse. This is keying me or making me think that it has a negative exponent to it. So I'm going to try this out. We said that this variable was W1. W1 tilde A. We type in x1 to see if there's a dependency. Clearly, that directly proportional doesn't work well. It requires an exponent. I said it appears negative, so I'm going to hit Shift 6 and give myself a negative exponent. I'm going to try, in this case, -1. And I see that that doesn't work so well. So the negative trend is okay, but not to that power. So I'm going to try one of the other exponents I used, maybe the square, maybe the negative square power works. And if I try that, I see the data fits perfectly. So this relationship here is actually a combination of two of these proportionalities, if we want to look at it that way. It's inverse, but it's also square. This would be called an inverse square proportionality. What we see here is that as this is getting twice as big, this is being reduced by a factor of 1/2 squared, which is 1/4. So hopefully through this lesson, you were able to see the different relationships and the different ways to provide the curve fit. Please refer to my reference chart to determine the curve fit before just randomly plugging in these exponents. I thank you for your time, and I do want to point out that I forgot to drag this one up here, so I will just finish off by moving this where it belongs. Oops, sorry, it's right below where it goes. All right. But overall, hopefully you were able to understand a little bit about how these graphs work and what they mean.